just needs a touch here and there. Well, first things first. I always say the place to hang a hat is on a hat stand. I much prefer seeing all of my face at the same time.
But there was nothing in it.
So in this classical knapsack problem, what you do is you imagine you have this bag here. You have some kind of a knapsack. And the knapsack has some maximum weight that it can take. What you want to do is try to stuff as much as you can into this knapsack, into this bag, up to, let's say, the weight constraint. Here the weight constraint is 15 kilograms. Each of the items you want to put in the bag have some value as well. Let's say you're trying to sell these items at a marketplace and you're trying to carry these things to the market. And you want to maximize the amount of money that you can make at the marketplace. Of course, it's not necessarily the case that the weight of the items corresponds to the value of the items. There could be some mismatches. Maybe some things weigh a lot more and have lower value. Some things weigh less and have a lot more value. So given the fact that you have this total weight constraint, what is the maximum you can achieve? What's the maximum you can pack this bag so that you can, subject to the weight constraint B. So assume that you have this capacity constraint B right here, some weight capacity constraint in the bag B, and you know a weight for every object, and you also know a value for every object. I want to emphasize it's really important that these both the weights and the values are integers, and we're actually going to talk more about that later on. It turns out this problem gets a lot harder if you allow arbitrary real values for the weights and the values. The running time is actually going to depend on the quantity B, so just wait for that. Another way to describe this problem is that you want to find a subset S of the numbers from 1 to n, where you maximize the sum over the weights, you satisfy, you have to have the sum of the weights in that subset be lower than the value B, and you want to maximize the total value in that subset. It turns out that the version that I'm showing you here is actually the kind of version 1 of the problem. That's the version where you don't allow repetitions. An object can either appear in the subset or not appear in the subset. There's another version of this problem where also you can imagine having multiple copies of every item, and in fact assume you have some unlimited supply of every item, and you can continue to add multiple copies of let's say item I for every I. This version right here, the one I'm describing here, this is version 1, right? This doesn't allow for repetitions. We'll actually look at both versions, but actually the version with repetition is actually going to be not much harder to understand and to deal with than the without repetition version. So stay tuned for that. Okay, so like a simple example, let's just imagine that you're trying to bring fruit to a picnic, and you have a basket that can only hold, let's say, 22 ounces of fruit, and you have these 4 different pieces of fruit, and let's say you have only one of each of these possible fruit types. Pineapples have a value of 15, grapefruits have a value of 10, apples have a value of 8, and limes have a value of 1. But of course, pineapples have a weight of 15, grapefruits have a weight of 12, apples have a weight of 10, and the lime has a weight of 5. So what's the most valuable pieces of fruit you can fit in the basket? What's the total maximum value that you can achieve in this basket subject to the weight constraint? Let's just consider a couple of ways we might try to fill this basket. You'll notice that the highest value item here is the pineapple. So we could try to take the pineapple, right? Put the pineapple in the basket. That has a weight of 15. We have a constraint of 22, so I've just taken out of the 22 units of weight in this basket, I've just used up 15 of them. There's only 7 units of weight left. There's actually only one more item I can put in the basket because the lime is the only thing that weighs less than or equal to 7 units. So I could put the pineapple and the lime in, right? I could put those 2 items in. That would give me a weight of 20, 15 plus 5, right? 15 plus 5 equals 20, and it would give me a value of, the value there is 15 plus 1 equals 16, right? And I don't have any room left. Now I've put, I've used up 20 of the 22 units. There's no other items that have a weight less than or equal to 2. So I've actually used up the total possible items that I can fit in this basket, and I'm done. I basically can either take the pineapple and the lime. I can just take the pineapple and the lime if I've decided to start with the pineapple. Okay, so now let's consider an alternative. An alternative would be I could instead go with the grapefruit. If I put the grapefruit in the bag, right, I could take the grapefruit. Now the grapefruit weighs 12. 12 out of 20 units. I still have 10 units left in the basket. What do I want to do with those 10 units? Well, I can either use the apple or the lime. The apple has a higher value, so clearly I'm going to put the apple in. So I can do the grapefruit plus the apple, right? And now I have a weight of, what is it? It's 12 plus 10, which equals 22, which is exactly the constraint that I have. And the value is going to equal, so what's the value? I'm going to take 10 plus 8 equals 18. And that actually has a higher value. 18 has a higher value than 16. So the better solution here is the grapefruit and the apple rather than the pineapple and the lime. You'll notice that what is called the greedy strategy here, we call it the greedy strategy, which is to say, well, there could be various ways to think about greedy strategy, but a very natural greedy strategy is simply to take the item that has the highest value density. What do I mean by value density? I mean, take the item that has the largest value per unit weight. And in that case, actually, the pineapple has the largest value density because 15 divided by 15 is 1. And if you look at the ratio of value to weight for all of the other fruits, they're actually all less than 1. The grapefruit is 10/12, the apple is 8/10, the lime is 1/5. So here we followed the greedy strategy, which is to start with the item. So our first attempt uses the greedy strategy. We took the item that has the highest value per weight, put that in first. But we actually ended up with a suboptimal solution. So your attempt to solve this greedily by just taking the highest value per weight items first isn't actually necessarily going to be optimal. To solve this problem optimally, actually, we're going to use dynamic programming. And I'll just emphasize again that it's very important that we had integer weights and values, and you'll see why that is in a moment. So now let's just try to solve this problem using a dynamic programming attempt. So let's just go ahead and give it a shot, okay? So the first thing we have to do to use dynamic programming is to try to come up with what the subproblem is, right? That's always the hard problem, is figuring out what is the subproblem, and then, of course, defining what the recursive relationship is for those subproblems. So if you had to have a first guess over what the appropriate subproblem should be here, one thing you might try to do is use the strategy for the, let's say something like the longest common subsequence or longest common substring or longest increasing subsequence, which is to try to have a subproblem that involves only the first, let's say, j many items available. So one attempt you might make is to say, let k of j be the maximum value achievable subset from only the elements from 1 up to j. And then we would have to try to find a recursive relationship for this k object, right? We would need to find some way that k of j depends on k of 1 through k of j minus 1. So the question is, can we find a recursive relationship? It turns out we're going to fail if we do it this way, but let's just go through and see why this isn't going to work exactly. We're missing one small thing that we need from this definition, but let's just give this a try. So if you were to follow along with this attempt, what you would presumably try to do is to break this k of j. You would try to reduce k of j to two possible cases. One is the case where you're not going to put if j doesn't belong in the optimal subset, and if j does belong in the optimal subset, then you're gonna get this expression. So if j doesn't belong in the optimal subset, then we can just forget j and then reduce to the case of finding the optimal subset up to and including j minus 1. And if the jth item does belong in the subset, then we are going to get value v sub j from it plus the optimal value subset up to and including the first j minus 1 elements. The problem with this case is that k of j doesn't tell us how much budget we've used up and whether there's any room left. So how do we distinguish between these two cases? So notice that there's this issue. How do we know which case we're in? The problem here is that we don't actually see this subproblem that we've defined. It doesn't give us any information about the nature of the remaining budget, and that's going to make us get stuck when it comes time to decide between these two different cases. So we actually have to consider something a little bit more sophisticated. What we need to do is assume that the knapsack subproblem we're trying to solve somehow encodes how much budget has been used up thus far. So let's give it another try. Okay, so for attempt 2, we're going to have actually a two-dimensional array. We're going to have an entry in the array for every pair b comma j. B is going to come from 0, 1, all the way up to capital B. That's the budget size, the integer budget size b. And j is going to come from 0, 1, all the way up to n. N is the number of elements we could possibly put in our knapsack. And again, I'll remind you guys, we're working on version 1 of the problem. So we're going to define a value k of b comma j. This is going to be our attempt 2 for the solutions to the bj subproblem. K of bj is going to be the maximum achievable value of some subset using only objects from 1 up to the jth object. And the total weight in this subset is going to be less than or equal to little b. Remember, little b is not the same thing as big B. Little b is some integer from 0 up to big B. Fix that bug. What we need to do now is figure out what should our recurrence relation be. What should our recursive relationship between these entries, k of b comma j, in this matrix? How do we define this recursive relationship? So that's our next step. Okay, so it's actually easier for me just to show you the answer and explain why this works out. We basically have to consider 3 cases. So let's just carefully dissect the 3 different cases that are embedded in this recurrence relation. Case 1 is if the weight of j exceeds the total allowable weight, then we can basically recurse to the j minus 1 case, right? If adding in the jth element is more than this little b, well, obviously can't include it because the knapsack can't even hold the weight of this object. So then we just recurse to j minus 1 case, and that's this case right here, right? So that case is when we recurse to just the j minus 1 case, because we obviously don't have space to include w sub j. Now there's the second case, which is similarly sort of easy. If the jth item simply wouldn't be used in the optimal value subset subject to the budget constraint, maybe j just isn't going to be in that optimal subset, in which case we also don't have to consider it. So if j simply doesn't appear in the opt subset, then we can also recurse. And this case is right here. Right? And we'll be able to check to see whether it is the optimal case or not. We don't know that just yet. But now let's look at the third case. The third case, if, let's say j is actually in the optimal subset, right? J is actually going to be in the optimal subset of elements subject to this budget constraint little b. If j is in that subset, then we can simply assume that it's in it, add its value to the quantity k of bj, and then again recurse to a smaller element in this table. But the question is, what smaller element do we have to recurse to? So if j is in opt subset, then A, add value to k of b comma j, and then B, we want to add value to the value v sub j, and then reduce the total budget by w sub j, and then we can just recurse to the j minus 1 case. So you'll see that this case right here is what is happening over here, right? We're simply adding the value v sub j to the total, right? And we're subtracting off w sub j, the weight. We're now adding this element j in, so we have to consider budgets now that are wj smaller. We have to reduce the budget capacity by wj. And then finally, we just recurse to the case for j minus 1, right? If the optimal subset includes the jth element on the first 1 through j items, then we can simply remove it, subtract the budget constraint by wj, and consider the optimal subset on the j minus 1 smaller elements subject to this smaller budget constraint. And that's why this recurrence works, right? We just consider these 3 cases. You'll notice that I had to do a maximization between these 2 cases. That's because we don't know in advance whether j should be in the optimal solution or should not be in the optimal solution. But that maximization takes care of considering both possible cases. Cool. All right, we probably just want to make sure we don't forget about the 2 base cases. There are 2 important base cases here, right? We need to remember that k of 0 comma j, that always equals 0. If you have 0 budget capacity, then you can't fit anything in the knapsack. So you know that the optimal solution is going to have 0 value because you can't fit anything in there. Even if you allow for, I guess this assumes that all of the weights of all the items are positive, but you generally would assume that yes, the weights are always going to be strictly positive. So if all the weights are strictly positive and you have a capacity constraint of 0, then you can't fit anything in, so you're going to have 0 value. The second, this is for all j. The second base case is the k of b comma 0 is also going to equal 0 for all j. For all b, I mean. And that should be straightforward. If this is saying what's the best subset you can take that has all of the items from nothing, right? The 0 means that you're not including any of the items in your subset. Even if you have a budget capacity of b, you can't include any items because the subproblem says, what's the largest, highest value subset you can make out of the first 0 items. There's no items you can choose from, so the base case is going to be 0 here. So those are the 2 base cases. We have to fill in those 2 values in the table before we start. So let me just show you this this dynamic programming strategy in actual what I call PySuedocode, and of course I call it PySuedocode because this isn't actually pseudocode. This actually is workable Python. I even tested it on a few examples just to make sure. But the code is actually quite simple. It's what you would already expect. You initialize an array of size b plus 1, comma n plus 1 if you have n items, and a budget constraint of capital B. And then for j and from 1 up to n, you're going to fill in the array starting with j, and then you're going to loop through the possible values of b from 1 up to capital B. First, you check if you're going to exceed the weight constraint of adding item j. You'll notice here I'm indexing with j minus 1. That's because Python I have to index this array with, it's 0 indexing, so I have to start with a 0 and go up to n minus 1. But if the weight of this item exceeds little b, which is sort of the kind of intermediate budget constraint little b, then I simply recurse to the j minus 1 case. K of b comma j is going to be equal to k of b comma j minus 1 because I can't fit the jth element in this subset. Otherwise, I have to consider 2 other cases. One is the case where J is not included in the optimal subset. I don't know in advance if it should be included in the optimal subset or not, but what I can do is I can consider all of the optimal subsets from 1 up to J minus 1 with the same budget constraint B. Right? This considers all of the cases where J is not included in the optimal subset up to some budget constraint B. Or I can consider the case where J is included in the optimal subset, and I add to consider that case. I add the value of this item J plus K of B minus the weight we had to remove to consider this new capacity constraint, since now we're assuming that J is going to be in the optimal subset, again on the remaining J minus 1 elements. So this maximization considers both cases and takes the best of them, so it can check whether J should or should not be in the optimal subset. And in the end, the final thing that it returns is little k of capital B comma n, which is, again, the largest value subset using capital B as the budget constraint, and the subset can come from all 1 up to n items, right? All of the items, not just the first J, but all of them up to n. So this pseudocode works. This Python code works. You can run it if you like, and this is basically just implementing the algorithm that we described on the previous slide. We should just quickly talk about the running time of this algorithm. You'll notice that we had to do this initialization of an array on this, which has size n plus 1 times b plus 1. That's an operation on the order of n times b. And then we had 2 loops. One was a nested loop. We had a loop of size that had to do n iterations, and inside of that we had to do b iterations, capital B iterations, and then inside we had to do a maximization, or do check a couple of things. But inside the 2 nested loops, we had basically an O of 1 operation. In total, the running time of this whole thing is on the order of n times b, and you'll see now why the size of the budget is kind of important here, because it factors into our runtime and will affect how fast we can run this algorithm. So remember how I said from the beginning that there were actually 2 versions of this problem? One is the case where you have only exactly 1 copy of every item, and you can only include it once. The other version is you can actually allow arbitrary amounts of repetition of these items. Let's say you have an arbitrary large number of pineapples, an arbitrary large number of apples, an arbitrary large number of limes to put in your basket to take to this picnic. That was version 2 of the problem. So you can define 2 different types of pseudocode to solve both of these problems. Here I'm calling this knapsack with repetition and knapsack no repetition. I don't know if you can glance at this. Can you find the actual, other than the name, can you find the line in the files that are different? If you just stare long enough at this pseudocode, you might not even be able to find where there's actually different. It turns out the difference is only in 2 characters. You'll notice that over here, and when we allowed repetition, when we had with repetition, with the no repetition, we had a j minus 1 here, and then it turns out that when you suddenly allow with repetition, you suddenly have this j minus 1 going to a j. Let's try to describe how this small change allows you to have repetition. Consider cases where you can repeat the same element multiple times. So again, this is our original case, and this was the case that allows repetitions. That's the only differences in these 2 characters that were added here, j minus 1. So let's consider why this works out. So if you recall, what we discussed before was that in the case where we consider this scenario in which you were trying to build the optimal subset of elements using budget constraint small b, and you had to ask yourself, is the jth item in that optimal subset? And first of all, if there's enough capacity to include w sub j, if w sub j is less than or equal to b, then we can consider adding it to the subset. So we consider 2 cases: either we add it to the subset or we don't add it to the subset. This was the case right here where we didn't add it to the subset. Right here, we said, you know what? If it's not going to optimally appear in the subset, then let's not add it. But in the case where we do actually want to add it to the subset, which is this case over here, what are we going to do? Right? Before we said, well, if we do include it in the subset, add it to the subset, subtract its weight from the budget little b, add its value to this value k right here, and then recurse on the j minus 1 elements. The thing we need to change here is that just because we were able to add the jth item to this subset, right? When we're considering the case, should we add the jth item to the subset, we could also add it again, right? We had to consider the case where we could actually even add another copy of j. So we actually don't want to recurse to a j minus 1 case here. In this case, what we want to do is just recurse back to the j case. Now, of course, you might be a little bit nervous about that. Generally, you don't allow recursing back to instances of the same size, right? You have to recurse to something smaller. But it turns out that that's okay because this problem did get smaller. We subtracted a weight w sub j, which we know is strictly positive, from the budget little b. So we are recursing to a smaller instance, just not in the j regime. This says that we can consider the case where we added the value of j to this to the maximum sum. We considered now finding the optimal quote-unquote subset on a smaller budget capacity, but we're still allowed to consider adding the jth element again, right? We're still allowing subsets that include elements from 1 up to j. And of course, these aren't really subsets because they could include copies of the item j. But again, that's the only change we needed to make to consider this second version where we're now allowing repetition of the items. That was that one small change that basically fixes everything.